Okay, fine. So team, you can hear me, right? Okay, I'm assuming you can hear me. So this session, we will start with dynamic programming. So dynamic programming is a very powerful algorithm design technique that can be used to solve a wide variety of problems in polynomial time and space, right? So a lot of problems, when you solve them in a naive way, in a straightforward way, it leads to exponential time and space. Exponential time, right? So it can be 2 power n, it can be anything of the form a power n, n factorial, something like that. All these are exponential functions. Okay, now, or super, it can be super exponential also. So you can reduce a lot of, reduce the time for a lot of problems to polynomial time. Polynomial time using a powerful algorithm design technique called dynamic programming. Okay, so here in computer science department, Professor Bender, so usually considers dynamic programming as a magical wand that can turn stones to gold. So it's that powerful, right? It's an extremely powerful algorithm design technique. If you attend interviews by Google and many other companies, Google, right? They ask very hard questions in interviews, right? And some of the topics that are very favorite to Google are recursion and dynamic programming. So they ask a lot of recursion-based algorithms and also problems that are related to dynamic programming. So it will be tremendously helpful if you practice, right, understanding and solving a lot of dynamic programming problems. So one is definitely for interviews, and another is just for the sake of it, right? It's beautiful. And the core idea of dynamic programming is very simple. The first is definitely recursion. You need to model the solutions as recursive algorithms, and then you store the solutions of subproblems. That's it. It's not a complicated idea or anything, right? But modeling the problem as recursive subproblems or recursive solutions is complicated. Okay. So here we will follow a template, and that template has been used for, I don't know, 35 plus problems. And that template is typically not found in all these books and all, right? When we were working on dynamic programming problems, we found that it is better to teach, learn, and practice solving dynamic programming using this template. And here, so in around 450 plus slides, right, that template, the same template has been used for every DP problem. Okay, of course, we will not cover all these 35, 40 problems. We will probably cover, I don't know, around 10 problems. A lot of them are simple problems and a few slightly complicated ones. Okay. Now, let's start with dynamic programming. So what is dynamic programming and why is it important? It's an algorithm design technique. We have learned several design techniques, right? Exhaustive search, decrease and conquer, divide and conquer. This is the next design technique we are learning. And next we have backtracking, branch and bound, so on. Okay, let's think about all the previous design techniques that we have seen. Decrease and conquer, it is based on recursion. Divide and conquer, it is based on recursion. Exhaustive search, though we wrote a lot of programs or algorithms in a non-recursive manner, you can also write recursive programs for exhaustive search. I mean, think about DFS and BFS. What did we do there? We recursively called DFS function. We recursively called BFS function, right? So even exhaustive search can be written. It can be easily understood using recursion. Okay, so in all techniques that are dependent on recursion, what is the core idea? You have a subproblem. You can consider a problem or a subproblem, whatever it might. So consider a problem. You split it into multiple subproblems, right? You split it into multiple subproblems, one or more. In decrease and conquer, there was only one subproblem. Remember? In divide and conquer, we had two or more subproblems. Okay. Then, like, how does dynamic programming fit in? Okay, let's draw a diagram, right? Probably that will help. So you want to understand this difference. This is very important. Okay, so a problem of size n was reduced to either say n minus c or n divided by c in decrease and conquer, right? This is decrease and conquer. Decrease and conquer. Okay, so we saw another design technique, that is divide and conquer, where we split a problem into multiple subproblems. Let's say this. Say C number of times, right? C number of times. Or yeah, it can be anything, but for simplicity, we will assume C number of times where C is greater than 1. See, if it is 1, it's just this, decrease and conquer. So if it is greater than 1, we called it divide and. Okay, where does DP fit in? So in DP, what happens is you have a subproblem. So you have a subproblem here. And maybe more. So it is dependent on a lot of subproblems. See, n dash, n double dash, n triple dash, so on. But they have they are kind of overlapping subproblems. So what do you mean by overlapping? So think about divide and conquer. In divide and conquer, we typically had independent subproblems, right? Independent subproblems. That means this has no relationship with another subproblem, right? Think about merge sort, think about quick sort. The left half is kind of independent with the right half. So the computation can go on with the left half and right half separately, right? So what about matrix multiplication? Yes, we divided into quadrants and we computed different quadrants individually, separately. There was kind of no relationship. We could have run them in parallel, right? Independent subproblems. What about this? So here you break a subproblem into multiple subproblems, right? And they have overlapping. That means there is some commonality. That means later in this stage, you might hit n double dash again. See, n double dash is encountered here. N double dash is encountered here also. Maybe n double dash will be encountered here also, right? So the meaning of overlapping subproblems is you visit a subproblem again and again and again and again multiple times. What about this? Think about this. Suppose you are dealing with, say, merge sort. You were sorting from 1 to 16. Suppose the subproblem was, say, 2 to, let's say, 3 to 4. 3 to 4. We will touch this subproblem exactly once. We don't need to sort this 10 times, right? We will sort it only once and we are done, right? So we visit a subproblem exactly once in divide and conquer. I mean, decrease and conquer is not relevant here, right? Because there are no multiple subproblems. It always decreases, so it should be unique. Divide and conquer has multiple subproblems, hence we are analyzing it. So each subproblem here will be touched only once, will be processed only once, and executed only once. What about here? So here, if you look at a problem and its subdivision, so it can happen that we might encounter the subproblems again and again and again. And this property is called overlapping subproblems. Right? So when you break a problem into multiple subproblems, if they are overlapping, it means this. You might have to encounter or process it again and again and again and again, right? So that is where DP can be applied. So what do you mean by DP? So the first time you are computing this n double dash, you compute it, right? Compute it, fine, process it, and store it. For the second time, third time, fourth time and all, if you encounter this subproblem n double dash, do not compute it. Just use the stored value, right? That's it. That's your dynamic programming. Okay. The first time you encounter a subproblem, you will execute it, you will process it, you will compute it. The second time or later onwards, if you encounter the same subproblem, you will not execute it. You would have stored the value, right? Stored the result, stored the solution of that subproblem. Use it again and again and again, right? So that is your D. I mean, think about your hash table. What is hash table? You compute something and store it in your hash table. I mean, that's a data structure, but now think about the algorithmic part of it. You are reusing the stored value again and again, right? For many algorithms, just using hash table itself is dynamic programming, done. Okay, makes sense? Okay, now think about your browser. You watch a video on YouTube. The first time you watch a video, that video has to get transferred from the server, right, router or server, to your computer. If you watch the same video for the second time and third time, it will not again download the video, right? The data will not get transferred from server to your computer again and again and again. What happens? It will be stored in a folder, right, called cache, and it will reuse it. So it will just run the video stored on your computer until you delete all the cache, right, or clear all the cache and so on. It will be there. So you will be using that hashed value, right? So it's like dynamic programming, right? The first time you execute something, you store it. The second time, third time onwards, if you encounter it, you will not execute it again. Instead, you reuse it. The concept of reusing, right? Okay, so if you were executing this again and again, it would have caused the tree to be exponential, right? But due to this extreme reuse, that entire subtree will be pruned, right? And that will become, constant time read of that result, right? N dash itself is a computation. Computation means it is a big recursion tree. But now you don't have multiple recursion trees. You have one tree rooted at n double dash, and for every other node that has this n double dash, that means the same subproblem, you can prune the tree, you can cut the tree and reuse the result, right? That means you're cutting off all those computations, the tree of computations. Just because of this multiple pruning, the exponential time algorithm will now be polynomial time algorithm. Right? Okay, we will see the examples later. But you got the heart of dynamic programming, right? This is the heart of dynamic programming. Right?
So I have a quick question.
Yes.
So, I understand, this does, great for reducing time complexity. But, if we have like n, let's say we have n subproblems that we, that we'll store the value for, don't we have to now worry about the additional space complexity? Because we'll have to store like n values as well, so the space complexity now increases as well.
Space complexity can increase, right? However, the increase will still be polynomial. You are okay. I mean, suppose I give you this pair, right? Suppose I give you something like, let's say 2 power n, right? N and n squared, or n squared, n squared. Okay, that's fine. So which one would you choose?
Yeah, well, if my computer can handle it, n squared, because it doesn't depend on how much, I guess, how much memory and stack space your processor has.
True. But even if you have enough memory, right? Probably this will take multiple years or centuries to, right? Finish for even n is equal to 100 or say 1000. Right? So this will never solve the problem, even for small instances. That's the power of an exponential function. Right? Yeah.
So basically, the increased stack space isn't comparable to the decrease in the time complexity by going from exponential to polynomial.
Exactly. This increase is not a lot, and there are complicated techniques to reduce this also, right? In most of the cases, you can reduce the space by one dimension lesser than the time, right? But sometimes it can be complicated, but we will not cover that in these DP lectures, but it is doable. You can reduce one dimension of space. You can shave off one dimension from n cubed to n squared, right? N squared to n, something like that. So you can shave off one dimension, but still it can be, I mean, depending on the problem, it can be still larger than your naive solution, but that's okay. That is still okay, right? When space is a serious problem, when you have, say, n power 4, n power 5, and all that, but n and all, we use it for sorting all the time. So sorting also requires n. So n is no big deal, right? N squared also, right? If this is good enough, n squared also is, decent enough. But if you have exponential function, right? And we have seen, even, so I think in one of the sessions I said 30 factorial, probably you will not be able to generate 30 factorial permutations on your computer, right? The time taken for this is so large, right? You will not be able to achieve. So these exponential, functions are like that. Maybe try out for 2 power n. If n is equal to, say, let's say 100, what happens? right? Probably you will not be able to solve the problem. But n squared is 10,000. If n is equal to 100, n squared is mere 10,000. 10,000 is nothing, right?
Yeah.
Right?
Yeah, I
So,
get it. Thank you.
yeah, substitute these numbers in check, right? Even you can extend it to n is equal to 1,000. 1,000 is still 1 million. 1 million is also nothing. But the first algorithm will definitely not be able to solve the problem. Okay.
Thank you.
Right. Okay. Now we understood the core idea of DP, right? Whenever you have overlapping subproblems, you use DP. Okay. Next. Now let's look at this concept, table filling. So what do I mean by table filling here? So typically what we will see in the problems in these slides, right? It's not always table filling. There are some problems where you cannot fill the DP. There is no concept of a DP table. You need to use a hash table and all. But for most problems, it's a table. You will store the results in the cells of a table. It can be a 1D table, 2D table, 3D table, whatever, but a table. So here a table means an array or a matrix, a 1D array, a 2D array, a 3D array, 4D array, whatever. But a table or array or matrix or vector of vectors all mean the same here. Okay. Lists, lists of lists of lists, they all mean the same. Okay. So the idea is in all these problems, we will see that the solution of a subproblem is just one cell of this DP table, DP array, right? The solution of the entire subproblem is just one cell. So probably 1, 1 means a solution of one subproblem. 1, 2 represents the solution of another subproblem. So here I'm just giving the position numbers, right? Row 1, column 2, row 1, column 3, and so on. But you will store the values here. Okay, so on. You will fill the table, and maybe the actual solution to the entire problem might be this last cell, or it might be this, or it might be this. I mean, it depends on the problem. I mean, we cannot have a final say. It is problem dependent. Okay, so here we considered a 2D array, but it could have been a 1D array or a 3D array, whatever. Okay, so it's just table filling. But how do we fill the table? So here we fill a cell, right? We fill the table cell by cell. Okay, how do we fill a cell? A cell is the solution to a subproblem. And we said solution to a subproblem. Okay, solutions to this problem is the combination of solutions to this subproblem and this subproblem, right? These are the child functions. So that means, see, this subproblem might also represent a cell. This subproblem will also represent a cell. So you write to this subproblem, right? Reading from this. So this is the read subproblem or read cell 1. That means you're using the result of this and the result of this subproblem. Okay, read cell 1. Let me write it as read cell 2. Read cell 2. So every cell depends on 2 or more cells of the DP table. So it reads from 2 other cells that are already written. So using the answers there, you compute another empty cell. Okay, so this relationship between a cell, a right cell and read cells itself is the recurrence. See, this is also a recurrence. How a problem is related to its subproblems. How do you use the solutions of the subproblems as the solution to the original problem? That is the recurrence. And these subproblems, we said they are just cells in a DP table. So how a cell is written using cells from using other cells in the same DP table. Okay, so DP, you can consider it's all about table filling. Table filling. Right? That's it. You just need to think about how to fill a table. That's it. That's your DP. And I believe you have understood what a cell represents, right? A cell represents the solution to a subproblem. And why do we represent it as a value in a cell? The reason is the first time we compute that subproblem, we store the solution to that subproblem in that cell and reuse it. Every time we see, that cell might be read multiple times. That's the meaning of reuse, right? The first time, see, you are only writing to a cell once. You can read from a cell multiple times. Writing to a cell means whenever you compute that cell, you write to it. So you are computing a cell once, you are writing to that cell once. I mean, the final answer once. You can partially update it again and again, but you are completely updating it only once. But reading from a completely filled cell, unlimited number of times, right? There is no limit. I mean, depending on the problem, it can be you can touch a cell log n number of times or n squared number of times, whatever it can be. It is problem dependent. You can read from a cell multiple times, but you write to a cell only once. Writing means execution, computing it. Reading means reusing the result. You're reusing the stored result, right? See, we are cutting away recomputations and using the stored result, right? Hence, we are storing it in a cell and reading it again and again and again, okay? So this is the strong relationship between DP, overlapping subproblems, recurrence, table, cells, so on, right? All these are related. Next. So a recurrence at a very high level, right? It's just a relationship from one subproblem or solution to a problem with the solutions to its subproblems. So that recurrence, that recursive relationship itself is called a recurrence. It's just a recursive relationship, okay? Now, once you have this recursive relationship, you can implement that in multiple ways. Suppose you do not use a table at all, right? You can just consider each subproblem as a separate function. You call it again and again. You execute it again and again. You process each subproblem whenever it is called again and again. That's a normal recursive algorithm. You're not storing anything, right? That's a recursive algorithm. And then, so there are two types of DP, top-down DP, bottom-up DP. We will not look at top-down DP, okay? So top-down DP means your call will start from at the top level, say problem of n, and you compute the solutions or the solutions to subproblems whenever required. Only if it is necessary, you compute it. Else, no. right? So top down is like, suppose you're working on a project, you learn the topics whenever required, right? It's that top down approach. Okay, so from problem one to you go to problem, say base case, say one. So this is top down. So what is bottom up? So bottom up is like, suppose you are working on a project, right? You start with all the background information, you finish all the background information first, right? It can be on probability or linear algebra and so on, right? And then you attack the final problem, right? So that is bottom up. Suppose you started computing the solutions of problem 1, problem 2, problem 3, problem 4, so on up till n. In that manner, if you execute or find the solutions to subproblems, that is called bottom-up approach. See, some of the solutions might not be useful at all. Intermediate solutions might not be useful at all, but still you will compute them because you started from the smallest to largest. You compute everything in between, right? Suppose you finish all linear algebra, probability, and then do your project. Many times a lot of concepts will not be used and still we will learn, right? That is bottom up. But top down is execute or compute it or learn something only whenever required. Okay, so here we will see the bottom up approach, because bottom up approach typically gives you a bit more a better speed up compared to top down. Okay, next. So coming up with DP, right? Once you have the recurrence, implementing the DP is no big deal, right? You don't need deep thinking or brain to execute, right, a recurrence, right? It's not really that hard problem. The hardest problem in DP, the headache in DP, is to come up with the recurrence, right? Finding a recursive relationship with the subproblems, that's a biggest headache. How do you define the subproblem? How do you define the recursive relationship between subproblems, right? That is coming up with the recurrence itself is, right, the 99% big problem, right, in DP. And implementing a given recurrence will not be that hard, right? If you practice a bit, right, it's not that hard. We will see. Okay. Now, bottom-up DP is typically fastest in practice. Fine. Now let's see the differences between these, right? Okay. Recursive algorithms will use recursion. Top-down uses memoization. We will not go deep into top-down. So bottom-up uses tabulation. So tabulation, you already know, it uses a table, right? A matrix, array, lists of lists or arrays of arrays, whatever. Okay, recursive algorithms just uses recursion. That uses, right, trees and all that. Okay, so how many times will a subproblem be computed? In a recursive algorithm, it can be computed greater than or equal to 1 time, minimum 1 time, right? You might hit that subproblem again and again and again, and every time you recompute it. So there will be a lot of recomputations here. So what about top-down DP? In top-down DP, every subproblem might be computed 0 times or 1 time. So why 0? Because if that subproblem is never used for your final answer, you will not compute it, right? So 0 times or 1 time. Okay, what about bottom up? Bottom up, every subproblem will be executed exactly once, whether you use it or not. Okay, fine. Next, computation graph. So if you draw a graph for all the computation, that means relationship between problem, subproblem, and all that, you will see a tree. That's why it is called a recursion tree. Recursion tree. What about DP? DP, it's not a tree, it's a DAG. Okay, why is it a DAG? You know what is a DAG? Directed acyclic graph. We looked at DAGs in topological sort, right? We said that if a graph contains cycles, there is no topological sort. There is topological sort only when the given input is a directed acyclic graph. It should be acyclic. And what's the difference between a tree and a DAG? Every tree is a DAG, but every DAG is not a tree. That means trees are subsets of DAGs. Okay. Next, coding. Right. Okay, leave this. Let's go to complexity. Complexity, recursive algorithms typically are exponential time algorithms, exponential time solutions. But DP, whether it is top down or bottom up, are polynomial time, right? Because both of these versions or variants, top down or bottom up, will not recompute. It cuts off all the recomputations. After cutting off the recomputations, it's just thinking about, whether should we go from n to 1 or 1 to n, right? Top down or bottom up, right? But both are not recomputing subproblems again and again. So here is the 7-step template we will use, right? We will always go with this 7-step template. For every problem, these are the 7 steps, right? We will give the problem statement in step 1, right? Problem statement, the exact problem statement, may be examples. If we want to understand the problem a bit better, everything will go to step 1. The second step, right, is coming up with the subproblem. See, here we shouldn't aim to get the algorithm itself. See, this 7-step process or template framework is constructed in such a way that you are thinking how to design dynamic programming algorithms should be in this way. You should not think about the recurrence before thinking about the subproblem. You should not think about the algorithm before thinking about the recurrence, so on, right? This is like the topological sort. You have to follow this order. And it is so beautiful that once you apply this again and again, your first aim when you get the problem is you will go for subproblem in a logical manner. You won't jump around directly to algorithm, right? Because you cannot come up with an algorithm without a recurrence. You cannot come up with a recurrence without a subproblem, right? So hence, it's good to go in this logical step-by-step manner because you know exactly how to attack a problem. So typically what happens is in textbooks and all, they just explain the algorithms without focusing a lot on recurrences. Then, so it feels to the readers that, okay, we should directly jump to the algorithms. But though the books teach a couple of algorithms, but it will not teach how to design dynamic programming algorithms, right? But that thinking of problem solving, right, is more important than giving a couple of solutions. So here we want to teach how to solve new problems. Okay. Step 2 is subproblem. You need to formalize what a subproblem is. Subproblem, as we discussed already, it is one cell in a DP table. One subproblem is equal to one cell. Another subproblem is another cell. So you need to rigorously define this cell in the DP table. Okay, that is step 2. Step 3 is the recurrence. Think about the recurrence next. Do not jump to the algorithm. So what is a recurrence? So recurrence tells you how a write cell depends on the read cells. That means how a cell must be written by reading from which other cells. So that the identification of the read cells will tell you the recursive relationship. right? This itself is the relationship. So this itself is the recurrence. So that's your recurrence. And I have highlighted this step in red because it is the brain of DP. For a lot of tiny problems, it might be trivial, but the real DP problems, right? People write papers just to identify the recurrence. If they just identify the recurrence, they write papers on those problems. Sometimes I can show you if you're interested, sometimes of 65 pages long, right? Very hard with a full of mathematical details proving that it is correct. Right? So recurrence, coming up with recurrence is the brain of DP. Okay, so subproblem is nothing but a cell. Recurrence is nothing but a relationship between cells, right? How to write one cell using other cells. And dependency, the same recurrence, the dependency is shown in a diagrammatic way here. Show a diagram. That is dependency diagram. So instead of dependency diagram, I have just written as dependency. That means show a diagram, because using the diagram, it helps you a lot in thinking about how the recurrence is, having a visualization of the recurrence, and that will help you in thinking about how to execute the algorithm. It will give you more ideas about the algorithm steps and so on. So write the diagram. Okay. Step 5 is the algorithm. Algorithm means the pseudocode. Here I mean the pseudocode. Pseudocode. Once you have the recurrence, it's not difficult to come up with the algorithm, right? It's not difficult to come up with the algorithm or the pseudocode. We will see that later. It is trivial. In fact, probably, I mean, I also wanted to do this. Probably, I believe it is possible to write a software, right? That can automatically give you the pseudocode or even the implementation in C, C++, Java, Python, whatever, given a recurrence. That is doable. So coming up with a pseudocode from recurrence is trivial. This is where thinking is required, right? All the other things can be automated. This can be automated. Yeah, so here also, right? Thinking is required, and I do not see a trivial way to automate these step 2 and step 3. It is still art, but this is science, right? This is pure science. This can be automated. So coming up with pseudocode is trivial. Okay. Next, once you have the pseudocode, write it in Python or any particular programming language, implement it, and get the table itself, right? So what is a table? That is dependent on the input, right? Depending on the input, you can get different tables. So once you have the implementation and run it on a specific example, this is a specific example. For a particular example, for a particular input instance, what is the DP table, right? Next, because understanding the example will also make sure that you have understood the recurrence properly, right? Okay. Next, complexity. Complexity is very trivial. So here we give time complexity and space complexity. I will give you a very quick way. Probably you can find a complexity in maybe less than 10 seconds, right? You can find it in 10 seconds. So there is a very easy way to compute complexity from the recurrence. So that's why I said, if you have these two, which requires a lot of thinking and genius, but the next 4, including the pseudocode and complexity, is automated, can be automated, right? It is trivial. Okay. Next, let's go to the simplest example, Fibonacci number. You know about Fibonacci numbers already. And we have seen a lot of algorithms also to compute nth Fibonacci number, right, in recursion. So let's start with step 1. Okay. So I won't repeat these steps again and again, but I'll just say that. Step 1, problem. So here we want to find the nth Fibonacci number. Okay. So one more thing. For every problem, I have also given a link here. Okay, so when you visit these PDFs, you can click on this link. It will take you to Geeks for Geeks website, or maybe some other website that will have the complete problem statement. Okay, just click on this. You will get the complete problem statement and other details, right? Subproblem. What is a subproblem? Subproblem is one cell of the table, right? What is a DP table here? It's the Fibonacci table. So what is the ith cell here? It's the ith Fibonacci number, right? So a subproblem is nothing but this, f of I. F of I is the ith Fibonacci number. Okay, let's use square brackets and not parentheses. The reason is typically we use this to mean a function. Function, that means this is the function name and I is the parameter. But what do we mean by this? This means it is an array value, right? It can mean a stored value at index I, right? So it can mean an array, or it can mean a hash table where I is the key and many other things, right? But the core idea is it means a stored value, a square brackets. But normal parenthesis, it means a function, because this is the style we use for normal procedures, right? Functions and all. So here always use square brackets. F of I is ith Fibonacci number. We want to compute the nth Fibonacci number. So f of I is the generic subproblem. And compute f of n. F of n is the objective subproblem. Our aim is this. Our goal is this. So you should always have two sentences. One is for the generic subproblem, general or generic subproblem. See, f of I means if I is equal to 0, you get f of 0, f of 1, f of 2, so on. But what is your aim or goal? Goal subproblem is f of n, right? So you should always have two sentences. Okay, next. Our goal is f of n. And what is the recurrence? The recurrence you know already, because Fibonacci numbers, we have studied this before. Ith Fibonacci number is I minus 1th Fibonacci number plus I minus 2nd Fibonacci number, right? Ith Fibonacci number is the sum of previous two Fibonacci numbers if I is in the range 2 to n, right? So you cannot have I is equal to 1 and you are calling this recursive function. Why? Because you need to have two base cases. The base cases are I is equal to 0, I is equal to 1. That means you know that f of f0 is 0, f1 is 1. Hence we have written f of 0 is 0, f of 1 is 1, and f of 2 is, apply this recurrence, right? F of 3 is, again, apply the recurrence. F of 4 is given by the recurrence up till f of n. So this is a generic subproblem. See, in the previous step, we defined what the generic subproblem meant, the meaning of f of I. And here we are computing that f of I. Okay, so understand the difference between step 2 and step 3. Step 2 is we identified f of I is the subproblem and we gave the meaning to it. What do you mean by f of I? In step 3, we are relating f of I with some other cells of the DP table. So this is, you are writing, this is the right cell, you are writing to f of I by reading from, these are the read cells. Reading from f of I minus 1 and f of I minus 2, right? Write cell and read cells. So this is your recurrence. This recurrence you knew already, right? This itself is DPL, right? Okay. Now, If you want to visualize it, the way we will visualize it is you draw the table for f of I. I mean, you can add all this, right? This is f of I. The right cell will be written in red color. The read cells will be written in blue color. So this will be f of I. This will be f of I minus 1. This will be f of I minus 2. Right? See, this can never be the right cell. Why? Because these two are the base cases, right? This is F0, this is F1. The red cells can be in this region only. But what is our aim? This is the ith Fibonacci number or the generic subproblem. Our aim is this. We want to compute f of n, right? Nth Fibonacci number. So we have a loop from I is equal to 2 to I is equal to n. Compute it using the recurrence. Done. Right? Anyway, so in dependency, just show the diagram, and you can also highlight what is f of I, what is f of I minus 1, and so on, right? Next, algorithm. So algorithm is simple here. F of 0 is 0, f of 1 is 1, and you have a loop. See, you have a loop. And how do you easily get the pseudocode from the recurrence? It's given here. You have a loop. I is equal to 2 to n. Repeat this. Done. Right? You should always get the base cases first. So f of 0 is 0. F of 1 is 1. And recursion case, loop, I is equal to 2 to n. Apply this. Done. Right? That's your pseudocode. See? It's no big deal. And return f of n, because that's your objective. You always return the objectives of problem, right? So return f of n. Done. Table, you know this table, right? This is for, say, all numbers I from 0 to 10. Okay. Complexity nn.
Professor,
Yes.
I think the table has a problem that there is a misalignment because you define the F1 as 1, F0 as 0. It's not a big deal, but I think
oh,
maybe
I
you
see,
want to
Right.
correct it. Yeah.
So we should have taken from this one, right? 0, 1, right?
Yeah.
Yes. We started from 1, 1, but it should have been from 0, 0, 1. Yeah, I mean, you can shift all these by 1. Very good catch, right? Very good catch. Okay. Now, let's see how to compute time and space. The last step, right? Time and space. It is trivial. Okay, let's look at space first. Look at the indexing. How many indices are there? So in this problem, there is only one index. If there is only one index, you will use a 1D array, correct? 1D array means n space. Done. Okay, how do you find the time? Okay, it's a 1D array, right? But each cell, look at the time taken for each cell. It's constant. So number of cells into time taken per cell, n times O of 1 is O of, right? Or say theta of n. Time. Right? So you can generalize this idea to every other DP problem. We will see other DP problems also. Right? Make sense? So theta n. So as I said, I believe for almost every DP problem, you can shave off one dimension of space, right? So there is a way to reduce this space to theta 1. And we have already covered it in the recursion slides, remember? We don't need the entire array. We just need the last two variables. We can store it and reuse it. Okay, so we can always reduce the space by one dimension. I believe, right? Because every problem I have seen, this has worked, but I don't know if you can prove it for every problem. Okay, let's move on to another problem. So there is a mistake here. This shouldn't be called partitions. We should call it compositions. Okay, just replace this word by compositions. Now, what is the problem? Count the number of ways to express a number as a sum of 1, 3, and 4. You're given a natural number, right? N greater than or equal to 1. Your aim is to express n as a sum of 1, 3, and 4. Let's consider an example. You have 4 here. See, 4 can be written as 1 plus 1 plus 1 plus 1, or 1 plus 3, or 3 plus 1, or 4. See, all the terms here are either 1, or 3, or 4. Make sense? So how many ways are there? For 4, you have 4 ways. Similarly, given n, how many ways are there? Right? You should only make use of 1, 3, and 4, and you can permute them. Look at this: 1 plus 3, 3 plus 1. You can permute them. Can you permute 1 plus 1 plus 1 plus 1? No. I mean, they are the same numbers, right? If the numbers are different, then you can permute them. Okay? You can permute them if the numbers are different. So how do you count this? Now, let's look at the subproblem. Given I, suppose you're given I. See, here we want to find the generic subproblem, right? Number I, let C of I denote the number of ways of expressing the natural number I as a sum of 1, 3, 4, where permutations of these numbers are allowed, right? So on. So we just defined the subproblem, C of I. C of I is our subproblem. And you know, C of I, that subproblem, is a cell in the table. So how many cells will be in the table? It's a 1D array, so n. And our aim subproblem, target subproblem, is C of n. We want to compute C of n. So C of I is the generic subproblem. C of n is the goal subproblem. What is the recurrence? So recurrence is this. See, I'm showing you the recurrence. Now try to prove it. So what we are seeing here is C of I is focus on the recursive relationship. It is C of I minus 1 plus C of I minus 3 plus C of I minus 4. Now, can you reverse engineer and identify why this is true? Ideas?
I think here the I minus 4 is a reflection of 1. I minus 1 is a reflection of 4. And my I minus 3 is a reflection of 2.
I minus 3 is a reflection of 2 because we are not supposed to use 2.
I'm sorry, I take it back. So I mean, I minus 1 is a reflection of 1. I minus 3 is a reflection of 3. And I minus 4 is a reflection of 4.
Okay.
Something like that. I mean, because when see here, right? So when you got anything, then you can subtract it by 1, right? So if you subtract it by 1, then that's just the one possibility, right? That's one way, right?
Okay.
Then
And then
when you subtract it by 3, right?
Mhm.
What you get is say it's I by 3, I minus 3. So I minus 3, you have only one possibility.
Very
That's
good, very good.
I
Okay,
minus 3. Yeah,
very
something
good,
like
very
that.
good. Very good. So let's take a simple example, right? From the example, we will generalize. Suppose you want to find the number of ways, right, to express say 100. Okay, number of ways to express 100 as a sum of 1, 3, and 4. How do you write it? So you can write it as, think about it, number of ways. Oh, okay. So what I will do is I will do something like this. So right. So number of ways to express 99, number of ways to express what 100 minus 3, 97, number of ways to express 96. Why? Well, let's think about it. So 100 can be written as 99 plus 1, correct? 100 can be written as 97 plus 3. 100 can be written as 96 plus 4, right? So these are the only terms you can use, right? 1, 3, or 4 to get 100, isn't it? If you use 1 as the last term to get 100, then you need to recursively compute, right? How to create 99. If you consider 3 as the last number to find for 100 or to compute 100, all the remaining numbers should form 97. If you use 4 in 100, right, you need to use 1, 3, 4 again to make 96 recursively, right? So you are recursing on 99, you are recursing on 97, you are recursing on 96. Make sense? That is the reason. See, so this implies if you have used 1, right? I mean, let's assume that 100 is a coin, 100 is the value to be created, and you have 1 cent coin, 3 cent coin, 4 cent coin. Okay, so you can use, if you use 1, you need to create 99. So find the number of ways to create 99, that is C of 99. Make sense? If you use 3, now you need to make 97. So how many ways are there to make 97? C of 97. So C of I minus 3 here. So similarly, if you use 4 cent coin, the remaining amount to be created is 96. So recursively compute, I mean, how many ways are there to create 96? Right? Make sense?
Professor, I have a question here actually.
Huh.
So here we can do the permutation, right? So actually my question is why it's 99 plus 1, then why is okay for 3, like why you don't count 97 as 3 plus 97? You just count 97 plus 3.
90, okay, repeat again, 97.
So the question here is, since if you go back to the last slide, right?
Mm-hmm.
the previous slide, you see here, when we count 4, we have 3 plus 1 and 1 plus 3. We treat it differently.
Okay.
So that means permutation, right?
Right.
So now see here, we consider 97. So 3 plus 97 should be different from 97 plus 3.
Oh, no. That is not required. Okay, let's take this example, right? Maybe here itself.
Yeah.
So if we do, say C of 4, let's start doing C of 4. C of 4 is the number of ways is how many?
It's 1.
Let's add
Let's
1
say
to
cannot
it.
go, right? Say you must be larger than 4. Probably you can
Okay.
take 5.
See, if you use 1 as the last coin, right? 1 cent coin, what a remaining term is, say 3, right?
Yeah.
Okay. If you use 3-cent coin or 4-cent coin, what happens here?
It's
So
say
this
C
is
1, right?
C of 1, and this is C of 0, right?
C0 is not defined.
Okay. So C0, oh, like we can only use it for 4 and 2, right? Correct.
Probably 5.
I mean, we could define it also if we wanted. Let's see, if C of 0 is defined as 0, then one plus 3, 3 plus 1. Okay. Okay, let's take 5, right?
Yeah, we can use 5.
Yeah, maybe 5 would be okay.
Yeah.
So 5, if you use 1 cent coin, if you use 3-cent coin, if you use 4-cent coin. Okay. Now, so you get C of 4, right?
Yeah.
C of 4 here, C of 2 here, C of how many?
1.
1 here.
Okay.
Now, did we reach the base case in any of these?
Yeah, 114.
Okay, 114. So C of 1, what is C of 1?
It's just 1.
And why is it 1?
You have only one way, right? So just 1.
One way, right? Only one way. So C of 1 means you're only using 1. There is only one way. Okay.
Yeah.
And next C of 2.
Yeah, just 1. Just 2 ones.
Is it 1 plus 1?
Yeah, that's
Okay.
just 1.
So
Just
1
one
plus
option.
1.
Yeah.
Okay. Next, what about C of 4?
That's 4, right? Right here.
C of 4, right. So we have all these, right?
Yeah.
Okay. Maybe we can write all these. See, 1 plus 1 plus 1 plus 1, 1 plus 3, 3 plus 1, 4. So let's assume this is already computed for simplicity.
Yeah.
Now what do we get? C of 5, we have 1 plus 1 plus 1 plus 1 plus 1. See, I'm adding all these and appending it with 1.
Yeah.
Okay. So then 1 plus 3 and then 1. 3 plus 1 and then 1. Oh, I made a mistake. 3 plus 1 and then 1.
Okay.
4 and then 1. Correct?
Yeah. And 1 plus 4, right?
1 plus 3. See, 1 plus 1 plus 3.
Yeah.
And 1 plus 4. 4 plus 1 is already defined. 1 plus 4.
I see.
Make sense? See, the permutation, we don't need to permute these ones.
Okay.
See, what this means is that the ending value is 1. So it will consider all these cases. Ending value is 1. This subproblem considers all cases where the ending value is 3. Oh, this should be 1. right? This considers
got
all
it, got
cases where the ending value is 4.
it.
But when we recurse, it will automatically make sure that as multiple values, all values are allowed at every position, the permutation is considered.
Okay, thank you.
Make sense? Okay. So got it? So finding the recurrence is a headache, right? This is the toughest part. See, once you identify how the ith subproblem, that is C of I, is related to other cells or other subproblems like this, right? You can take some examples, to derive these recurrences. Okay, so you always use examples if you want. Or maybe you can also think about directly attacking it. Suppose you're finding I cents. Either you can do, right, I minus 1 plus 1, or I minus 3 plus 3 cent coin, I minus 4 plus 4 cent coin. So the number of ways to compute this recursively, the number of ways to compute this recursively, the number of ways to compute this recursively, right? Okay.
Hi, Professor. Can I understand this as if um permutation is actually being taken care of in each subproblem? So as long as I exhaust all the possible ways of each subproblems,
Correct.
the problem will be self-resolved, right?
Correct. See, if you consider all possibilities at each step, automatically it is, related to permutations, right? See, if you had considered 1, 3, 4, I mean, you would also have considered 1, 3, 4 at the starting point. So
Yeah.
look at this, 1 plus 3, 3 plus 1, right? So it's like permutations only, right? Okay. So one more point I wanted to say here. Okay. So now, how do you find the number of base cases? Recursion is fine. How do you find the number of base cases? Base cases here are 4. How did you get 4? In Fibonacci, we had 2 base cases. Here we had 4. In another problem, we might have 100 base cases. How do you decide? What you need to do is look at your subproblem. I. Now look at the longest jump it has to make in history. The longest jump in the past, that means it has to see 4 units back in time. 4 units in the past, right? Hence, there are 4 base cases. So this is the longest jump in past or history. Make sense? Okay, so hence there are 4 bases. These 4 bases can be solved, using your hand and paper, right? In a normal way. So try to get it in a normal way and then have this recurrence relation. Okay, so always first get the recurrence relation. From this recurrence relation, that means this recursive relationship, get the number of base cases. Once you get the number of base cases, then you can define the base cases, right? Then your recurrence will be complete. So do not try to write all the base cases first, because you don't know how many base cases you need, right? Without looking at the recursive relationship. Okay, dependency. C of I depends on C of I minus 1, I minus 3, I minus 4, right? Okay, next. The pseudocode is simple, right? I will skip this. Table, complexity. Okay, again, trivial. Okay, I will skip this problem. This is not required. Let's move to tiling problem. So here is the problem. You have a board of size 2 cross n. So there are 2 rows and there are n columns, right? So this is a board of size 2 cross n. And you have these kinds of tiles, 1 cross 2 tiles or 2 cross 1 tiles. 1 cross 2 tiles means this. 2 cross 1 tile means this. 2 rows, 1 column. And here 1 cross 2 means 1 row, 2 columns. You have 2 types of tiles. Now what is the question? You have to use these tiles and tile this board of size 2 cross n, and you want to find the number of ways to do this tiling, right? How do you find the number of ways in which you can tile this board using 2 types of tiles? Okay. Now, can you tell me what would be the subproblem? It's 2 cross I, right? Where you have I number of columns. So let's define the subproblem C of I as number of ways to tile a 2 cross I board. So that means that the meaning of this is we will compute C of 1, C of 2, C of 3, so on up till C of I, so on up till C of n. Right? To tile a 2 cross I board using 1 cross 2 or 2 cross 1 tiles. And our aim is to compute C of n. See, we don't need to give 2 as a parameter here, right? Because 2 is a constant. It's not, right? It's not a variable. So no need to write C of 2 comma I or anything. It's just C of I. Now, here is the recurrence. And the recurrence is very similar to Fibonacci, right? So what is your Fibonacci recurrence? F of I is f of I minus 1 plus f of I minus 2. And the claim is that even this recurrence, recursive relationship is same. C of I is C of I minus 1 plus C of I minus 2. Can you prove it? How do you show that this is true? Okay, see, I have given you the recurrence. Now, can you prove that this recurrence is true? What is your logic? How do you think here, right? So yeah, go ahead.
So here, if you consider C I minus 1, right, you have only one possibility to fill the last row, but last column. That's 2 by 1.
Uh-huh.
Then you consider I minus 2, then you have only one possibility to fail. That's to use 2 row of 1 times 2.
I see. Okay. Okay. So, like, what is the summary?
So, I mean, in summary, so when it comes to I, you can combine C minus 1 and C minus 2 because each contributes 1 share, right? Like,
Right. Okay, let's draw a diagram, right? So suppose
yeah.
this is 2 cross I, right? 2 cross I columns here. Okay, I don't need to write 2, right? But that is default. Every problem will have two rows. Now let's think about how we can tile this from the end. See, in DP, always try to think from the end, right? So you have I columns. So try to tile it from the end. Then you can call recursion. See, you can tile it this way. You can tile it this way, right? or you can tile it using two 1x2 tiles. See, this is one tile, this is one tile, or this is one single tile.
Yeah.
Do you agree? This is type 1 tile. So here you have used two type 2 tiles, horizontal tiles, but two of them. But this is vertical tile, you have only used one such vertical tile. Make sense? See, if you use a single type 1 tile, what happens? The number of columns reduces by 1. If you use these kinds of two type 2 tiles, what happens? The number of columns reduces by 2. Correct? Right?
Yeah.
So these are the only ways in which you can tile from the end. Is there any a third way? There is no third way. So the number of ways of tiling this, right, 2x I board, is same as the number of ways of tiling this left side and the number of ways of tiling this. Left side has I minus 1 columns, that is C of I minus 1. Right side, the number of columns is I minus 2, so the number of ways to the number of columns is I minus 2, right? So the number of ways to tile this I minus 2 column board is C of I minus 2. Right? This is anyway C of I. So C of I is the sum of these two. Number of ways, right? Number of ways. The left side, right side. We do not care about what type of tiles we are using, how many of these we are using. We don't care because that's not in the question. The question says how many possible ways are there to tile. The question is not how many type 1 tiles are used, how many type 2 tiles are used, what is the total number of tiles. No. Right? Make sense? So does this make sense?
Yes, it's just hard to wrap your brain around the first time you see it.
Right. So initially, right, when you're learning dynamic programming initially, you want to make sure you read as many programs as possible, right, recurrences as possible, and reverse engineer, decode the meaning of it. So try to decode the meaning of it or reverse engineer from the recurrence, what is the intuition behind it. Okay, in I would say stage 1, right, as a student. You learn as many recurrences as possible and decode the meaning. In the second stage, so that should happen for at least 50 problems. You should do this for at least 50 DP problems. Then you will get a hold on DP. And then onwards, you should try solving new DP problems. I mean, really serious ones, right? Solving in the sense, how do you come up with the recurrences, not just taking the recurrence and understanding it, right? Decoding. Reverse engineering, okay, you can do it for say 10 to 15 problems, but next say 50 problems you should try to come up with recurrences, right? So as I said before, this is your subproblem C of I. Always try to start from end. That's what we did in the coin problem also, right? 4. We said let the last coin be 1 or 2 or 3 or 4. And then we looked at the remaining and we recursed. Here also, we tiled from last. There are two ways in which we can do. and recurse. That's it. Right? Tile it from last, add coins from last, and recurse. Make sense? Okay, let's move ahead. And dependency, same as Fibonacci, just the base cases are different, right? There we had, I think, 0, 1. Now we have 1, 2. It doesn't matter. The numbers will be very, very similar. Okay, complexity, same. Okay, I think we will stop here. We will continue in the next session.
Professor, I have a question.
Yes.